Good day everyone, my name is Ron and let's answer some thermodynamics problems. Calculate the power requirement of the pump when 40 tons per hour of water with a temperature of 293.15 Kelvin has to be pressured from 1 bar to 6 bar. Assume the efficiency of the pump is 70%. Input your answers in the text box below and briefly discuss the answers obtained. So to start, we need to know the given and required. So this is the diagram of the pump. The inlet conditions, as stated earlier, is 1 bar pressure, 40 tons per watt of water per hour of mass flow rate, and 293.15 Kelvin of temperature. And the outlet is 6 bar, and we don't know the mass flow rate nor the temperature. However, we can assume that this simulation is at steady state, and this means that the mass flow rate inlet is equal to the mass flow rate outlet, meaning that the mass flow rate of outlet, or M2, would be also 40 tons of water per hour. Then, the details of the pump. As stated earlier, its efficiency is 70%, and what we need to find is its power requirement, or how much electricity or energy does it need for it to work under these specific conditions. Then, we need to solve using DWSIM. To assist in our solution, 40 tons per water, or the tons unit, does not exist in DWSIM. Therefore, we need to convert the tons into kilograms. As such, to assist in our simulation, 1 ton equals 907.185 kilograms. Therefore, 40 tons of water equates to 36,287.4 kilograms. Then, to start off, let us now go to DWSIM. We create a new process model. Then, we need to set our boundaries and conditions. So we click Next. Then, remember that the substance being discussed is only water. So we'll put here just the substance of water. We type the substance water. That's the only component being manipulated. Then we click Next. Then, since water can be a liquid and a gas, and water is usually used in turbines and pumps for movement, we use the steam table as a property package of main use. Next, for the systems of units, we need to choose a customizable one, since that the units on DWSIM is different from the units given in the problem. So going back to the problem, it says here 40 tons per hour of water, but we converted already into kilograms, so that means the mass flow rate will be in kilogram per hour. Okay, then the temperature must be in Kelvin's unit. So we'll put here Kelvin. Next, the pressure must be in bar unit. So we'll put here bar. And we'll also put the pressure difference as bar. Then that's all needed. We will finish. Then we have our set information. Afterwards, we will pick the pressure changer. We need to pick a pump since that's the unit operation of focus. Magnify. Then, before we start everything, we need to first rename our respective sheets, our respective streams. So this is the inlet, so we'll rename it as inlet. Then this one is outlet. And this one is power requirement. And we can just rename this as a pump. Okay, for the inlet conditions, going back to the problem, it is said to be at 1 bar. So we'll put here 1 bar. Initial temperature is at 293.15 Kelvin. 3.15 Kelvin. And its mass flow rate is calculated earlier, which is 36,287.4 kilograms. So 36,287.4 kilograms. Alright, everything is set. Then there's no need for compound and round since water is the only thing needed here. Afterwards, we go down to the pump. So, one of the requirements of the problem is that the outlet must be 6 bar. So the calculation type would be outlet pressure must be at 6 bar. Then the efficiency must be at 70%. Therefore, we'll put here 70%. And that's it. The DWSIM automatically calculates the needed parameters, and what we need to find is the power requirement. And according to DWSIM, the power requirement is 7.21 kilowatts. However, the main question is, how is this answer reliable in a physical or an actual sense? Well then, going back to the PowerPoint, I will also try to solve this using hand calculations. To assist, we need to make some assumptions for the system. We need to, as said earlier, it is at steady state, meaning the mass flow rate in is equal to the mass flow rate out. Constant flow speed, meaning that liquid speed does not change as it goes in and out, meaning that this delta change in kinetic energy is equal to 0. We also show that it is at constant height, meaning that a pipeline from pump and another pipeline is at the same height, let's say ground level, meaning that at constant height, the potential energy is also 0. And since the mass flow rate is in a per hour time denominator, we will also assume a 1 hour of operation. Then, we need to also discuss the details on the specific unit operation. So there are different unit operations such as turbines, pumps, compressors, so on and so forth. And for pumps, these are its specific details. Its work is consumed, meaning that electricity is needed for it to function. Without electricity, it will not work. Therefore, at a chemical engineering sense, the consumed work must be at a positive value. Then, with that in mind, consumed power, which is also a function of consumed work, must also be in a positive value. A consumed power's formula is simply the shaft work, or the consumed work, multiplied by the mass flow rate. The minimum consumed power is using this formula, same formula, such that the shaft work is at isentropic conditions. And unless the problem states that there is heat release, we will assume that the pump works adiabatically, meaning Q equals 0. And lastly, the pump efficiency. The pump efficiency equals the minimum power required over the power actual. Then we substitute the formula for the power. Then we cross out the mass flow rate sign. So this means that the pump efficiency is also equal to the shaft work at isentropic conditions over the shaft work at actual conditions. To start our calculation, we must remember the steady state open system energy balance for one inlet and one outlet equation. So using this equation, then we say that EK, or kinetic and potential energy, is 0. The process is adiabatic, so it's also 0, and shaft work is positive. We'll receive this formula H2 minus H1, meaning the enthalpy at the outlet minus the enthalpy at the inlet equals the shaft work. Then rewriting the formula in terms of isentropic details, we found out that the formula reforms into that the enthalpy at outlet at isentropic conditions minus the enthalpy at the inlet at actual conditions equals to the shaft work at isentropic conditions. Next, there is a saying in the book of where this problem is based, Introduction to CH Thermodynamics edition by Smith, Van Ness, Abbott, and Srivastava. They say that the values of the enthalpy of compressed or subcooled liquids, and these are seldom available. Hence, we cannot just simply go to a steam table and figure out the inlet conditions. Due to the fact that the inlet conditions are at subcooled properties, it is hard to find due to their seldom available data. Therefore, how do we solve this by hand? We will go back to the fundamental property relation of enthalpy. You can find this in the same book as said earlier, CH Thermo 8th edition, referring to equation 6.9, where the differential of enthalpy is equal to the temperature times the differential of entropy plus the volume times the differential pressure. If we assume isentropic conditions, meaning that the inlet entropy is equal to the outlet entropy, or in other words, the change in entropy or the differential in entropy is equal to 0, we would have this equation, then integrating it with respect to enthalpy and pressure, and we also assume that for liquids, that volume is independent of pressure. So we put the volume outside of the integral sign, and we will have equation 2. So we say that the isentropic enthalpy at the outlet minus the enthalpy at the inlet is equal to the volume of the liquid times the difference in pressure. If you can notice that it has the same formula as the shaft work derived earlier and the earlier derivation of the volume and pressure difference, then we equate equation 1 to equation 2. Going back, equation 1 is this equation, and equation 2 is this equation. We equate those together since they have the same variable, which is H2 isen minus H1. This means that the shaft work for isentropic conditions can also be recalculated in the form of volume times pressure difference. Then, we need to convert volume into mass. Since, of course, our given is in mass form, we need to convert volume to mass. How do we do that? Well, remember that the formula for density is equals to mass per volume, or mass over volume in a mathematical sense. Rearranging that formula, we get volume equals mass over density. This means that the isentropic shaft work is equal to the mass over the density times pressure difference. Then, how do we find the density of water at that certain temperature? Well, we cannot just assume a certain density of water in Google. As chemical engineers, we need to be very thorough with our calculations. This means that we need to assume, not really assume, but we need to take note of every condition that the liquid is experiencing at this moment in order to assert a accurate result. So we need to find the density of water that as a function of temperature. You can see this formula from Perry's Chemical Engineering Handbook 9th edition, table 2-32, for temperatures between 273.16 Kelvin and 353.15 Kelvin for liquid water specifically. So it has this formula, and after inputting the formula using the temperature given and the inlet condition, which must be in Kelvin, I've calculated a density of the water at the inlet condition to be 55.4085 moles per cubic decimeter. Then, to find the isentropic power, so we have now the isentropic shaft work stated earlier. Then, in order to convert it into power form, remember that the power is simply shaft work times mass flow rate. Since in this formula, shaft work is equal to a function of mass, what happens if we change the mass into a mass flow rate term? Then, it will be a function of time. This means that shaft work will be turned into power. So, by changing just the mass into mass flow rate, the shaft work will be turned into the power unit. Then, we substitute everything that we know, mass flow rate, density, pressure difference, and a few conversion factors. I calculated an isentropic power of 5049.0067 watts. This means that the minimum amount of power consumed by the pump is 5049 watts. Then we need to find the actual power requirement for pump efficiency. Remember that the efficiency has the formula for pumps, the isentropic power over the actual power. Knowing that the isentropic power is 5049 watts and the efficiency is at 0.70, then we can just substitute everything and we have the value of P, which is 7,212.87 watts or 7.21 kilowatts. Remember what we calculated earlier in DWSIM is 7.21 kilowatts also, and our hand calculation resulted in 7.21 kilowatts. This means that they are very similar, hence our solutions for DWSIM and HAL calculations are accurate. So this means that we understood the problem correctly, theoretically, and accurately. Thank you.